Hello, this is David Hilster, critical thinker, dissident science, and if you are not science woke, then this is a place for you. There are literally thousands and thousands of scientists from around the world that have been working for decades outside the mainstream who have identified problems, fixed those problems, and who are proposing new theories and models. You're not going to find anything like this on YouTube, so you want to make sure you go right down below, right there, click on that subscribe button and little bell next to it, and you'll be alerted to when our next video drops. Hey folks, I know I've been off on a sabbatical for a couple weeks. Well, I was pretty sick with a fever and everything, but I am back and mad as heck as always, and giving you the latest of what's going on in my thoughts on the world of physics and cosmology, which is in a dire mess. But good news, folks, we have better models out there. I'm not just going to complain about it. We on this channel, remember, we always talk about other alternatives. So you, again, want to make sure you subscribe. And I thank all the new subscribers. And sorry I haven't been around, but I am back. And today we're going to talk about something that I've been wanting to talk about for a while and just haven't done it. And that is the electron. Now, the electron, when my father and I were looking at our model, where we say the electron, the electricity, gravity, light, all of those things, the magnetic field, are all the same particle because they all go at the speed of c, so why shouldn't it be the same particle? Well, I started to think about, well, what do we really know, for instance, about the electron? If we're going to replace the electron with another particle, a smaller particle actually, how can we do that? We want to make sure that doesn't make, you just can't go in and do that. So I started reading on the electron a while back, and folks, it's just as bad as all the other particles. In fact, it's got some even more problematic things that I believe more problematic than even something like the proton. So let's look at it right here. Here's a picture of it. You can see, I'm not going to enlarge that, but you have the SPD, and there's, of course, there's an F orbitals. Those are orbitals. This is the hydrogen atom, and this is hydrogen atom orbitals at different energy levels. And of course, that means different energy levels means that we have electrons flowing around. And of course, those little clouds and stuff give you an idea of its probability of finding one there. So you can imagine it's whirling around and whirling around there, if that's your type of model, and that's where you're going to find it. The less dense it is you're not going to find it at that position as often as you are in more dense. And of course, they've actually looked at these and sent electron microscopes to look at electrons themselves, and they actually see some of these formations. So they're pretty well established in the sense of what most likely is physically is going on. Of course, what the electron is what we're here to talk about. Let me switch to a different type of mode so we can see this, which is a more reading mode. And let's take a look at what they say the electron is with our critical thinking minds, so I can give you an idea of what I think about the electron. So electron is a subatomic particle, symbol E, to the minus sign because it's negative, or beta with a negative sign, whose electric charge is negative, is -1, and it says right whose electric charge is -1, elementary charge. And it says electrons belong to the first generation of the lepton particle family and are generally thought to be elementary particles. Now, what are elementary particles? Well, elementary particles are exactly that. They are said to have no subatomic particles. Now let's take a look at this problem. That means, again, there's no partless parts if you believe in infinity, and that is, okay, you have this electron, so there are no parts to it, so that means no matter how small you get and get close to it, you're not going to find a hole in it because it can't be made up of parts, and therefore you have the same problem you have in a non-infinity world. This is a magical particle that has magical things like an electric charge that's a negative. It's considered one elementary charge because we use the electron, so we say that's an elementary charge. It's just arbitrarily chosen because that's what we think the electron is. It has charge. So again, that's a magical power. If you don't have anything below it, and you have anything that you say, well, the electron is attracted to the proton because the electron is negatively charged, the proton is positively charged, and this causes force. Well, what is it? And it says, well, let's keep reading about what it says. So it says, right, are generally thought to be elementary particles because they are known there have no known components or substructures. So that means, well, maybe they think someday there will be, but not right now. The electron has a mass that is approximately 1/1836th of that of the proton, meaning the proton is the heavier part of atomic structure. That of a proton. It says quantum mechanics properties of electron include an intrinsic angular momentum, spin of a half integer. Okay, folks, here we go again. Here we get to this arbitrary attributes to arbitrary packages, including the electron. And I'm not sure even Alexander Unsker will agree with this part of it, but I am saying to you folks that there's angular momentum and a spin of a half integer value. Okay, if it's arbitrary, but is it really spinning? And if it's really spinning, what does that really mean? Again, we get into this really arbitrary stuff where a system, they put together a system and they try to explain stuff with it, but is it really what's going on? Well, we have lots of problems, of course, because charge, in our model, there's no such thing as charge. There's forces that cause things to go together. It's because there are real things causing real things to go together. All right, so we move on and we say, we see that a half integer value expressed in units of the reduced Planck constant. We won't even talk about Planck constants today. Not important for us right now. We're just looking at the electron. As it is a fermion, no two electrons can occupy the same quantum state. You know, that's, yeah, I mean, I guess there are places in modern physics where two things can occupy the same space. Not in any of my physical models there aren't. Like like all elementary, here's another one. Here we go. Like all elementary particles, the electrons exhibit properties of both waves and particles. And of course you get into the both waves and particle thing. That's the wave-particle duality. They don't explain why this is. They don't explain how it is. They just say, it's that way, it's weird, get used to it. No. Again, we have better models that you don't have these problems. Like my father has a solution to the wave-particle duality. So we don't have a wave-particle duality. There isn't a problem. An electron, it turns out to be there's a lot more particles than just one around a hydrogen. That's what we say. And that's why people sort of try to say, well, it's a wave, it's a particle, it's a wave. All right, so they can collide with other particles and can be diffracted like light. The wave properties of electrons are easier to observe with experiments than those other particles like neutrons or protons, because electrons have a lower mass and hence a longer de Broglie wavelength for a given energy. I don't even want to get into that. Not that interesting for us. Electrons play an essential role in numerous physical phenomena, such as electricity, magnetism, chemistry, thermal conductivity, and they also participate in gravitational, electromagnetic, and weak interactions. Since an electron has charge, it has a surrounding electric field, and if that electron is moving relative to an observer, it will generate a magnetic field. Now, whoa, this is a part where I want to stop a little bit and talk about here. First of all, since an electron has charge, an arbitrary concept, we give it to it. It says, since an electron has charge, it has a surrounding electric field. What's an electric field? Do you have an explanation for what that is? Because so far we have charge, one magical power, and we have electric field around it, which comes with it, I guess. It's there. What is it? They don't tell you. So again, what we have is a particle with magical powers. It's got a magical field around it. And we say, of course we know it's there because we measure it. Well, all the things we're doing in physics experiments and even electronics experiments and even the cathode ray tube, which is the old tubes that televisions were made out of, all of those things. You have assumption upon assumption upon assumption. And so when you do these experiments, you're saying, see, It is negative because when I put it through a magnetic field this way, the electron goes this way. Oh, and we found the positron, and the positron will go the other way because it's positively charged, and therefore we know because, well, you don't tell us what the electrical field is. You don't know how that. You don't tell us how it affects, how physically and why physically it bends anything like an electron or a positron. None of that is told to us. So again, when you read this, you have to understand. This is why we want to throw out most all of particle physics, because it's a mess. It's because it's got a lot of magical powers where we keep massaging him into things like, oh, it's spin, but it's a half a spin because the integer we sort of chose over here, we need to. It's all arbitrary, folks. So anyways, electrons radiate or absorb energy from photons when they are accelerated. Of course, this is from, again, experimentation. We have almost no explanation. Of course, we don't know what a photon is. We don't really know what light is. Is it a particle? Is it a wave? Again, it's a mess. Laboratory instruments are capable of trapping individual electrons as well as electron plasma by the use of electromagnetic fields. Let's see, we don't know what electromagnetic field is. So if we are trapping individual electrons in this, we don't know what we're doing. We don't know what we're doing. Electrons are involved in many applications such as electronics, welding, cathode ray tubes, electron microscopes, radiation therapy. That's sort of weird. Okay. Lasers, gaseous ionization detectors, and particle accelerators. They're used for all those things. All right. That's interesting. Interactions involving electrons and other subatomic particles are an interest in fields such as chemistry and nuclear physics. The Coulomb force interaction between the positive protons within an atomic nuclei and the negative electrons without also allows the composition of the two known as atoms, meaning you have electrons and protons. So that's what they're saying. This is part of what atoms are made up of. So absolutely, we agree with that. At least ionization of different binding energies. Well, we'll just keep going on. History: discovered effect of electric force. The ancient Greeks noticed that amber attracts small objects when rubbed with fur. Along with lightning, this phenomenon is one of humanity's earliest recorded experiences of electricity. And so, yes, we see this idea of what electricity is. There's this type of attraction. We see both electric and electricity are derived from the Latin electrum, also the root of alloy of the same name, which came from the Greek word for amber. So that's how it sort of started. Discovery of two kinds of charges. In the early 1700s, Francis Hauksbee and French chemist Charles Francois Dufay independently discovered what they believe were two kinds of fractional electricity, one generated from rubbing glass, the other from rubbing resin. So this is one of the things that, if you haven't seen it, go to Andreas Sees. Of course, then I'll put the link up there. Andreas Sees, which talks about electricity. I have several videos with him. So take a look at those, Dissident Science and Electricity. I've got some of his experiments I'm trying to do, but that's very interesting stuff. So yes, we did a lot of experimentation with all of this, and we were conjecturing what was going on, and the idea of electricity and electrons ended up coming up through history. And so we can keep going, moving. Discovery of free electrons outside of matter. Now, this is really important, of course, because if electrons make up atomic structure, and then they also are free to flow and do things, this, of course, has great implications on the world, the technical world of what we can do with things. And that's one of the parts of the history here that's very interesting, because they really talk about something later on, if I can go down here, and that is beams. So let me see if I can get down to the part where they talk about electron beams. In fact, I will search on that for us so I can get to the correct place quickly. Oops, I went too far. I was supposed to just do it on the page itself. Beam, B-A-A, bump. The beam's electron deflected by a magnetic field. Discovery is electron, and that's what people talk about as the beams. And the idea is that if for instance, we thought electricity was a wave, okay? Electricity was a wave through a medium, which of course etherists believe that's true. Electricity is a wave through some type of medium, then of course, we would not find individual particles that we would call electricity. We'd just say they are waves. But one of the big things that are said, including one of our scientists in our CMPS, who is Dr. Bill Lucas, he says that the reason we know something is a particle is because we can make a beam out of it. That's the idea. So a beam of electrons deflected by a magnetic field. That's what we're seeing here. And of course, that's what we say is happening in the cathode ray tube. And that's what we had in our early television sets, a beam of electrons that would hit a phosphorus screen and then excite that, and that would be kept lit for a little bit. And that beam would be deflected because we could control it with an electromagnetic field. And that's how we made our television sets. And if that beam, therefore, if it's a beam, it is a particle. That's what we are saying. But of course, that depends on your model. So furthermore, by applying a magnetic field, he was able to deflect the rays, thereby demonstrating that a beam behaved as though it were negatively charged. And again, this is where we talk about the electrons going one way, the positrons going the other way, which is the opposite of an electron, and therefore they're negative and they're positive, and that's where we get into our system that we build that we do not explain really what's going on. And one of the things I believe that myself and my father and many of us in the CMPS want to do is actually know what the heck is really going on. We're tired of systems, arbitrary systems, with arbitrary things like charge and electromagnetic fields and magnetic fields and all those things without anybody telling us what they are. Oh, light is a particle. Light is a wave. A graviton is a particle. Oh no, it's not. It's the bending of space-time. What's space-time? Oh, it's the Higgs field which pops in and out. No one's telling us what these things are at the very fundamental level, not even an electron. So anyways, we can go on and on and on, and we keep going down here, and then we start finding out, well, the electron and its quantum mechanics. We talk about quantum mechanics, of course, is what goes on at the very small levels with inside atoms, and we're looking at quantum behavior, which means, look, electron is going to be in a certain be moving around, but its possibility of where it is and where you'll find it's going to be more in what you see in these diagrams as the dense, like I showed you in the very beginning of this. And it goes on and on. Particle accelerators, when developed particle accelerators during the first half of the 20th century, began to delve deeper into the properties of subatomic particles. The first successful attempt to accelerate electrons was electromagnetic induction, and they talk about that again with a beam. They're talking about a beam and confinement of individual electrons. They talk about that, and of course here is the elementary standard chart of elementary particles here. Sorry about the little graphics there. The reason they have those funky check marks because that's transparent. This is just looking at the graphic itself. That means it's transparent, so if I put this on a black background, this would still show through. That's why you see those little things for those who are computer geeks. But a key, of course, you see down here, right here, the electron, that's a lepton, and these things they're not made up of other particles. And that's why you don't see down here, for instance, the proton, because protons are made up of these guys, which of course are quarks. And quarks, there are 6 of them. And they all look, quarks, they're all the same particle, really, because they're named the same and they're colored the same, and then they have just different names, but they got to be this. Can you see how ridiculous this is, folks? This is our particle world. This is a standard model of elementary particles in physics. We have gluons. You know what a gluon? It glues things together. We call it a particle. I mean, this is all just nuts. Oh, we got the Higgs over here. It's sort of like attached. But hey, that's worth a Nobel Prize. So you guys shut up and learn it, swallow your medicine, believe all this stuff, and you too will never be able to find out how this universe works. And of course, I'm Dave D. Hilster. I've been rambling on about this electron long enough. I'm happy to be back. I'm happy to be doing these things, and I hope you're enjoying this once again. And I'm doing this a little bit differently because I'm just going at it. I'm not even cutting and pasting anymore. Just going to take a look at these pages, go down there, and remember what I say. Don't take my word for any of this. Stay critical, stay thinking. I'm Dave D. Hilster. I am your science therapist trying to get you science woke. Ciao for now.